Okay, so let us continue with the previous lecture where we were discussing about even and odd signals. So we have stopped the last lecture at where we have stopped the last lecture, we have proved that so if you add two even signals, okay, so if you add two even signals that results in an even signal, and if you add two odd signals that results in an odd signal, and if you add an even and an odd signal, so the resulting signal will be neither even nor odd. Okay, so and also we have proved that what, so if you multiply two even signals, okay, so the resulting signal is an even, okay, and so if you multiply two odd signals, that also will result in an even signal. And finally we have seen that if you multiply an even signal with an odd signal, that results in an odd signal. Okay, so we have proved all this, so hopefully you are aware of this. Okay, so let us take few examples to demonstrate these results. Okay, so let us take few examples to demonstrate these results. Okay, so okay, right, so first here let us say we are talking about continuous time case, and here we are talking about, let us say, discrete time case. Okay, so first example I take for continuous time case to be x of t is equal to cos t plus t square. Okay, so here what is that we have taken, we have taken x of t to be equal to cos t plus t square. So what does it do? So this signal is an even signal and this signal is an even signal. So what happened, you are adding two even signals, so obviously the resulting signal will be in an even signal. How do you say that? If you replace x of t with, sorry, if you replace t with minus t, what do we get? Cos of minus t plus minus t whole square, again which is an even signal. So what do we get? We get x of t also to be an even signal. So let us see for discrete time case an example. So what is that? Here we will take x of n to be cos of pi n by 4 plus minus 1 power n. So here again what happens, this signal is an even signal and this signal is an even signal, so obviously the resulting signal also is an even. Again, how do you prove that? Replace n with minus n, so we'll get cos of minus pi n by 4, which is cos pi n by 4, and minus 1 power minus n is same as minus 1 power n, so again it is even. So if you add two even signals, so that results in an even signal. Okay, so now we will take one more example. So what is that? If you take x of t to be equal to t square sin t plus t cos t. So if you take t square sin t plus t cos t, so here what is it you see? So this signal is an odd signal, so this signal is also an odd signal. So if you add two odd signals, the resulting signal x of t also will be an odd signal. You can directly prove it. How do you prove that? Again replace t with minus t. What do we get? Minus t whole square is t square into sine of minus t is minus sin t. So I'll get minus t square sin t here. Again if you replace t with minus t, what do we get? Minus t cos of minus t, which is cos t. So obviously you will get x of minus t equal to minus x of t, which is an odd signal. Okay, so for discrete time, with what example we will take? X of n is equal to n cube cos pi n by 4. Okay, n cube cos pi n by 4 plus n sine 3 pi n by 4, n sine 3 pi n by 4. If you take an example, again this fellow is odd, this fellow is odd, so the resulting signal is also odd. Okay, so you can prove it again, that's easy. Okay, next, one more example. So if you take here x of t to be equal to cos t plus sin t. Okay, so this signal is even, this signal is odd, so obviously, so this, if you add an even signal to odd signal, the resulting signal is neither even nor odd. Similarly, for discrete time case, we'll take one more. What is that? X of n equal to cos 3 pi n by 7 plus sine 6 pi n by 11. So if you take this signal again, what happens? So this fellow is even and this fellow is odd. So obviously what will happen? The resulting signal is neither even nor odd. Okay, so resulting signal is neither even nor odd. So let us take this as page number 7. Okay, right. So this is as far as addition of two signals is concerned. Now we will take an example for, again we'll take few examples for what happens for multiplication. Okay, so we'll take examples for multiplication. So again we will segregate discrete time. We'll take examples for continuous time case and discrete time cases. Okay, so continuous time case this side and discrete time case this side. Okay, this is page number 8. Okay, so here which example we will take? Here again, first one, let us take x of t to be equal to t square sine square t. Okay, so t square sine square t. So we look at the signals carefully. T square is even and sine square t is also even. So here what you are doing, you are multiplying two even signals, so obviously the resulting signal is also an even signal. Okay, so here we will take one more example for discrete time case. So what is that? Let us take here x of n to be equal to 1 plus n square. So again this is a constant which is nothing but even signal, n square is also even signal, so obviously the resulting signal x of n is also even. Okay, so okay, right, so we'll take another example here. So if you take x of t to be equal to t cos t, so again what is this? Here we take this fellow, so t is an odd signal, cos t is an even signal. So if you multiply an even signal with odd signal, the resulting signal x of t is odd. Similarly here we'll take one more example. So what is that? X of n is equal to n cube into minus 1 power n. So here n cube is an odd signal, minus 1 power n is an even signal, so the resulting signal x of n is odd. Why? Because you are multiplying an even signal with an odd signal, so resulting signal is an odd signal. Okay, so here we'll take one more example. X of t is equal to t cube sin t. Okay, so x of t equal to t cube sin t. So here t cube is odd and sin t is also odd. So if you multiply two odd signals, so the resulting signal is an even signal. So what example we will take for a discrete time case? So here we take x of n to be equal to n into n cube. Okay, so n into n cube. So obviously n is odd and n cube is also odd, so the resulting signal x of n should be even. So that is clear. Why? Because n into n cube, so this is nothing but n power 4, which is easily seen to be an even signal. Okay, so what is that we have seen? So if you multiply two even signals, you'll get an even signal. You multiply, oops, so here we should have taken product of signals, right? Okay, so here we'll take the signal to be x of 1 plus n square into, let us say, cos pi n by 7. Okay, so obviously 1 plus n square is even, cos pi n by 7 is even. The resulting signal x of n will be even. I'm sorry for that. So I have taken addition here, but now that's fine, no problem. Okay, so these are some examples to demonstrate what we have seen as a note. Okay, so now let us continue with even and odd signals. Okay, so what does it say? In general, okay, so in general the signals are, okay, in general signals are neither even nor odd. Okay, so signals are neither even nor odd. Okay, okay, but what happens? But they can be split. Okay, so but they can be split into even and odd parts as follows. Okay, as how do you say, how do you split? First let us take for continuous time case and later we will see for discrete time case. So how do you split? X of t can be split as xe of t plus xo of t. Okay, so name it, so xe of t stands for even part of the signal and xo of t stands for odd part of the signal. So as name itself suggests, this is even part, so obviously this fellow should be even. So odd part, name itself suggests this fellow should be odd. So if we add even and odd signals, so my x of t is neither even nor odd. So but this can be split into even and odd parts like this. Okay, so where, so what are xe of t and xo of t? So we write them as where xe of t is equal to x of t plus x of minus t by 2 and xo of t is equal to x of t minus x of minus t by 2. Okay, so let us call this equation 1, let us call this equation 2, and let us call this equation 3. So it is clear that if you add these two guys, that is what xe of t and xo of t, if you add you should get x of t. So let us see that. So what happens if you add these two guys? I'll get x of t gets added to x of t, that is 2x of t, and x of minus t and minus x of minus t will get cancelled out. So I'll get 2x of t by 2, which is nothing but x of t. Okay, which is nothing but our x of t. Okay, so we'll take a very basic example to see that. So if you take, let us say, x of t to be equal to 2 cos t plus 3 sin t. Okay, so default the signal is neither even nor odd. Why? Because we are adding an even signal with an odd signal. So my given signal x of t is neither even nor odd. Okay, the given signal x of t is neither even nor odd. Okay, so but how do you find its even and odd part of the signal? So one method is to obtain the even part and odd part by inspection. So how do you say that? So because this signal is 2 cos t plus 3 sin t, in this 2 cos t is even, so obviously that should correspond to even part of the signal. Similarly 3 sin t corresponds to an odd signal, so it should be odd part of the signal. So that we do it by inspection, but let us follow the equations as above and evaluate the even and odd parts. Okay, so to evaluate them we require x of minus t. So what is x of minus t? So wherever there is t, put minus t. So 2 cos of minus t is same as 2 cos t plus 3 sin of minus t is same as minus 3 sin t. Okay, so for this, so this implies what? Xe of t will be equal to how much? 2 cos x of t plus x of minus t by 2. So if I add these two guys, what will I get? So 3 sin t will get cancelled out. I'll get 4 cos t by 2, which is nothing but 2 cos t. Okay, similarly what is xo of t? So xo of t is nothing but x of t minus of x of minus t. So this minus this will, what will happen? 2 cos t will get cancelled out. Total I will get how much? 6 sin t by 2 is there. So obviously this will be equal to 3 sin t. Okay, so that will be equal to 3 sin t. So we can do this by inspection and also with using the equations. Okay, so this is page number 9. Okay, so let us extend the same result to discrete time case. So how do you extend the same result to discrete time case? Okay, so for a discrete time case, so what happens? Again the signals are in general the signals are neither even nor odd, so but that can be split into even and odd parts as follows. So as usual, as the name suggests, so this corresponds to even signal, so this corresponds to odd signal. Okay, so where again xe of n is nothing but what? X of n plus x of minus n by 2 and xo of n equal to x of n minus x of minus n by 2. Okay, so let us call this equation 4 and this fellow to be 5 and this fellow to be 6. So as usual, what happens if you add xe of n with xo of n, you should get x of n. So that is clear from these two equations. If you add these two guys, I'll get 2x of n by 2, which is same as x of n. Okay, right. So we will take an example here for this discrete time case also. So what is that? Let us assume that x of n equal to n square cos of pi n by 3 plus 1 plus n square into sine pi n by 4. Okay, so obviously this fellow is in, so by inspection how do you find? Directly, so this fellow directly is an even signal and this fellow is an odd signal. So we can say that this is an even part of a signal and this is the odd part of a signal. But let us proceed by using the equation. So what will be our x of minus n? So wherever there is input minus n, obviously I'll get n square into cos of pi n by 3, and here if I put n with minus n, what will happen? 1 plus of minus n whole square is 1 plus n square into minus, so obviously I'll get minus 1 plus n square into sine pi n by 4 into sine pi n by 4. So for this, what is even part of the signal xc of n? So that will be equal to x of n plus x of minus n. So if I add these two guys, what will happen? Obviously these two will get cancelled out. I'll get 2n square cos pi n by 3 by 2, which is same as n square into cos of pi n by 3. Similarly, xo of n. So xo of n will be equal to how much? This minus this, correct? X of n minus x of minus n. So obviously what will happen? N square cos pi n by 3 will get cancelled out. So I'll get this plus this. So that will be 2 times 1 plus n square into sine pi n by 4 and divided by 2 is there. So what will I get? 2 gets cancelled out. I'll get 1 plus n square into sine pi n by 4. Okay. So by inspection also we got the same answer. Using equations also we got the same answer. Okay. So here one important note which we have to be aware. So let me call this page number 10. Okay. So what is that important note? Okay. So what is that note? If the signal is even, for example, if the signal is even, okay, so what will happen if the signal is even? So obviously what will it happen to its odd part? If the signal is even, its even part is what? Is the signal itself, correct? So the even part is the signal itself. And what is its odd part? And its odd part is 0. Okay, and its odd part is 0. Okay, so let us see with an example. So what is that? Let us take x of t to be equal to t square cos t. So this signal is clearly even. So for this, what is even part? So for this, even part is t square into cos t, which is nothing but the signal itself, but its odd part is how much? 0. Okay, so the odd part is 0. So similarly, if okay, the signal is odd, okay, if the signal is odd, so what will happen? Its even part is 0, correct? Its even part is 0 and its odd part is the signal itself. Okay, and its odd part is the signal itself. Okay, so even though here we have taken the example of a continuous time case, the claim is equally valid for discrete time case too. Okay, so here for this note we'll take one more example. So what is that? So let us take x of n to be equal to n square into sine of 2 pi n by 3. Okay, so clearly the signal is an odd signal, so obviously what will happen, so where this even part is 0 and its odd part will be equal to n square into sine of 2 pi n by 3, which is nothing but the signal itself. Okay, so this concludes the lecture on even and odd signals. So in this we have seen so the definition of an even and odd signals and so many properties of them, and finally we concluded with defining the even and odd part of the signal. So we will see many numerical problems later, and and the lecture 3 starts with conjugate and anti-conjugate and complex anti-conjugate signals. Okay, what do you mean?